1971 Chevrolet Vega 2.3-liter inline-4. The Chevrolet Vega's 2.3-liter inline-4 is remembered as one of the most infamous engines General Motors ever produced. On paper, it was innovative. An aluminum block with no cast iron cylinder liners, paired with an iron head. GM engineers claimed the use of a high silicon alloy would make the cylinder walls hard enough to resist wear without liners. In reality, it was a disaster. The problem started with heat. The engine ran hot under normal operation, and when combined with minimal corrosion protection, the block and head expanded at different rates. That caused the head gasket to fail repeatedly, allowing coolant and oil to mix. Once that happened, cylinder walls began to scuff and score, leading to rapid oil consumption and a constant blue haze trailing behind the car. Owners reported overheating, blown head gaskets, seized pistons, and oil leaks so severe they could ignite on contact with the exhaust manifold. Even careful maintenance couldn't save it. Once the aluminum surface was damaged, there was no easy way to repair it. Engines that survived more than 40,000 miles were the exception, not the rule. Chevrolet eventually tried fixes, improved head gaskets, better coolant flow, and even a cast iron sleeve retrofit, but by then, the Vega's reputation was ruined. The car became a symbol of 1970s Detroit shortcuts, and the 2.3-liter engine stood at the center of it. The Vega wasn't just unreliable, it was mechanically self-destructive. Its engineering flaw made it dangerous to drive when overheated and nearly impossible to trust. 1997 Ford 5.4-liter Triton V8 2-valve. The Ford 5.4-liter Triton V8 2-valve engine was meant to be a workhorse for trucks and SUVs like the F-150, Expedition, and E-Series vans. Instead, it became one of Ford's most notorious engines for mechanical failures that could turn routine maintenance into a disaster. The most infamous problem was the spark plug ejection issue. Ford's design gave each plug only 4 threads of contact in the aluminum cylinder head, far too few to hold under pressure. Over time, the threads weakened, and plugs could suddenly blow out of the head while driving. The result was a deafening pop, loss of power, and in many cases, coil and fuel rail damage. In rare instances, fuel vapors ignited, creating a legitimate fire risk. The problems didn't end there. The 5.4 Triton suffered from timing chain tensioner wear, camshaft phaser failures, and poor oil flow that led to top-end ticking and lubrication problems. Combined with brittle plastic intake manifolds that could crack and leak coolant, owners faced constant mechanical headaches. Ford eventually revised the cylinder heads with more threads and improved the timing components, but by then, the damage to the Triton's reputation was permanent. Even high-mileage survivors often suffer from chronic misfires and oil leaks. In its era, the 5.4-liter Triton was supposed to balance power and durability. Instead, it became a cautionary tale of poor engineering decisions, an engine that could literally blow itself apart. 2000 Chevrolet 2.2-liter Ecotec. The first-generation 2.2-liter Ecotec engine was meant to usher in a new era of modern 4-cylinder design for General Motors. Lightweight, efficient, and durable on paper, it powered cars like the Chevrolet Cavalier, Saturn Ion, and Pontiac Sunfire. But early production engines developed serious durability problems that often led to catastrophic failure. The most common issue was timing chain tensioner failure. The design relied on engine oil pressure to keep tension on the chain, but restricted oil passages and a weak hydraulic tensioner meant that lubrication could lag during cold starts. When oil pressure dropped, the chain would slack, skip teeth, and throw off timing. Once that happened, valves could strike pistons, a fatal event in this interference engine. Owners reported loud rattling noises before sudden stalling or complete seizure. Even engines with regular maintenance sometimes failed before 80,000 miles. In many cases, the first sign of trouble was too late to prevent damage. Oil sludge buildup and camshaft wear were also common, caused by limited oil flow to the top end. Overheating and head gasket leaks followed, often leading to coolant and oil mixing, a death sentence for the aluminum block. GM eventually revised the design in later Ecotecs with a better tensioner, improved oiling, and stronger chain guides, but early models remained plagued by poor reliability. The 2.2-liter Ecotec was supposed to modernize GM's small engine lineup. Instead, its early years became known for timing failure, noisy operation, and engines that could die without warning, turning basic commuting into a gamble. 2005 Ford 4.6-liter 3-valve Triton. The 4.6-liter 3-valve Triton was Ford's attempt to modernize its modular V8 for the mid-2000s. Used in the F-150, Mustang GT, and several large SUVs, it offered solid torque and decent efficiency. But under the hood, it hid a collection of design flaws that made it one of Ford's most frustrating engines to service. The worst issue came from the 2-piece spark plug design. Each plug had an extended shell that tended to seize in the aluminum cylinder head. When technicians tried to remove them, the lower portion often broke off, leaving metal fragments inside the combustion chamber. Extracting them safely required special tools, and if debris entered the cylinder, the engine could suffer serious internal damage. The 4.6 also developed timing chain tensioner wear and cam phaser failures, leading to loud rattling, poor performance, and inconsistent timing under load. Oil starvation from clogged passages only made things worse. Head gasket leaks and coolant loss were common on higher mileage engines, especially in trucks exposed to heavy towing or long idling cycles. Ford eventually replaced the Triton series with the more reliable Coyote engine, but the 3-valve 4.6-liter left a lasting impression on owners and mechanics alike. What should have been a dependable V8 for work trucks and muscle cars instead became known for broken spark plugs, ticking valve trains, and expensive repairs. For many, the 4.6-liter Triton 3-valve summed up the era's engineering missteps, a strong design undermined by poor details that turned ordinary maintenance into a gamble. 2002 Chrysler 4.7-liter PowerTech V8. The 4.7-liter PowerTech V8 was intended to bridge the gap between Chrysler's aging Magnum engines and a new generation of modern, modular designs. It powered Jeeps, Dakotas, Durangos, and Ram 1500s through much of the 2000s. On paper, it seemed like a solid mid-sized truck engine, compact, smooth, and capable of decent power. In reality, it became infamous for catastrophic internal failures that could end an engine in seconds. The most severe issue was valve seat fallout. Like its 3.7-liter V6 counterpart, the aluminum heads in the 4.7 used pressed-in valve seats that could loosen under high heat. When one of these seats dropped, it would fall directly into the combustion chamber, where it shattered pistons and gouged cylinder walls. The result was instant terminal failure. Oil maintenance was another Achilles heel. The engine had narrow oil passages and relied heavily on clean oil to feed its overhead camshafts and timing chain system. Missed oil changes or sludge buildup often led to timing chain tensioner collapse and camshaft scoring. Once that happened, the top end of the engine would seize. Cooling issues were common as well. Overheating from clogged radiators or failed thermostats could warp heads and cause head gasket leaks, often leading to total failure before 120,000 miles. Chrysler improved oiling slightly in later years, but the engine's reputation never recovered. For many owners, the 4.7-liter PowerTech wasn't a modern replacement. It was an expensive lesson in how one weak design decision can doom an entire engine family. 1978 Oldsmobile LF9 Diesel. The Oldsmobile LF9 5.7-liter diesel V8 is one of the most infamous engines General Motors ever produced. Born from the late 1970s oil crisis, GM rushed it into production to meet growing demand for fuel-efficient cars. Instead of designing a new diesel from scratch, engineers converted a gasoline 350 cubic inch Oldsmobile V8, and the results were disastrous. The gasoline-based block wasn't built to handle diesel compression ratios, which are nearly double those of gasoline engines. This caused head bolt stretching, gasket failures, and frequent cracked cylinder heads or blocks. The head gaskets often blew under normal driving conditions, allowing coolant and oil to mix and causing overheating or total seizure. Adding to the trouble, GM omitted a water separator in the fuel system, meaning even trace amounts of moisture in diesel fuel could corrode injectors and fuel pumps. The injection pump itself was unreliable, leading to hard starts, poor performance, and stalling. The LF9's weaknesses made it both unpredictable and dangerous. Sudden power loss on the highway was common, and in some cases, oil contamination caused internal fires. Many engines failed before 50,000 miles, and warranty replacements often suffered the same fate. GM attempted improvements with stronger bolts, revised heads, and the DX block, but the damage was done. The LF9 became synonymous with the collapse of GM's early diesel reputation, hurting consumer trust for years. The Oldsmobile LF9 wasn't just a bad engine. It was a mechanical symbol of corporate haste and engineering shortcuts, leaving behind one of the darkest chapters in American automotive history. 1992 Chevrolet 3.1-liter V6. The 3.1-liter V6, part of GM's 60-degree engine family, was widely used across cars like the Chevrolet Malibu, Pontiac Grand Am, and Buick Century. It was meant to be a dependable mid-range engine for millions of vehicles. Instead, it became known for one of the most common and costly mechanical failures of its era. The core issue was the lower intake manifold gasket, made from a plastic and rubber composite. It was prone to shrinking and cracking under heat cycles. When that happened, coolant leaked into the oil passages, contaminating the oil with glycol. The result was sludge buildup, bearing damage, and eventual head gasket failure. Drivers often first noticed a sweet smell from the engine bay, disappearing coolant, or a milky residue on the oil cap. If ignored, the problem escalated to overheating or complete engine failure. The leaks were slow but relentless, and because they were internal, they often went unnoticed until it was too late. GM issued technical service bulletins and updated the gasket material, but the underlying design flaw, poor clamping load between the heads and intake manifold, meant even repairs weren't always permanent. Otherwise, the 3.1-liter was simple and smooth, but the gasket flaw overshadowed everything else. For many owners, it was a slow-motion disaster, an engine that quietly destroyed itself from the inside out. Today, The 3.1-liter stands as one of GM's most widespread cautionary tales, a mass-produced engine undone by a $30 part that couldn't handle the heat. 1996 Chevrolet 3.4-liter V6. The 3.4-liter V6, a derivative of GM's 60-degree engine family, powered everything from the Chevrolet Venture and Impala to the Pontiac Grand Am and Montana. It shared much of its design with the 3.1-liter, but introduced its own set of durability issues that made it one of GM's most failure-prone engines of the late 1990s. The main problem stemmed from intake manifold gasket failures, nearly identical to its 3.1-liter predecessor. The gasket's composite material couldn't handle the thermal expansion of aluminum heads and iron blocks. Over time, the seal degraded, allowing coolant to leak internally into the oil system. The mixture formed sludge that attacked bearings, cam journals, and lifters, leading to catastrophic failure if ignored. Even when caught early, repairs were expensive, requiring disassembly of the top end to replace the gasket set. GM later released an improved metal core gasket and revised torque specifications, but many engines had already suffered permanent damage. The 3.4-liter also struggled with poor coolant flow and head gasket leaks, particularly in minivan and crossover applications that operated under constant load. Overheating was common, and many engines were scrapped before 120,000 miles. On paper, the 3.4-liter was a practical mid-range engine with modest power and fuel economy. In reality, it became a symbol of GM's late 1990s cost-cutting, an engine that failed not from abuse, but from its own materials. For countless owners, the 3.4-liter V6 turned ordinary maintenance into a cycle of leaks, overheating, and expensive repairs. It's remembered today as one of GM's most infamous examples of how a simple gasket design can ruin an otherwise competent engine. 2011 Chrysler 3.6-liter Pentastar V6. The 3.6-liter Pentastar V6 was introduced as Chrysler's all-new global engine architecture, designed to replace a scattered lineup of aging V6. It powered everything from Jeep Wranglers and Ram 1500s to Chrysler 300s and Dodge Chargers. On paper, it was a breakthrough, light, powerful, and efficient. In practice, early versions of the engine suffered from several serious design flaws that led to costly and sometimes dangerous failures. The most notorious issue was the plastic oil filter housing. The assembly, mounted near the engine valley, was prone to cracking and leaking under heat and vibration. When the housing failed, it could cause a sudden loss of oil pressure, starving the engine of lubrication, and leading to bearing failure or complete seizure. In some cases, the leak dripped oil onto the exhaust manifold, posing a potential fire hazard. Other problems included rocker arm and lifter failures, which caused persistent ticking noises and valve train wear. Some engines also suffered from coolant crossover leaks and camshaft phaser issues that led to rough idling and stalling. Although Chrysler addressed these problems with updated housings, metal filter adapters, and revised cylinder head designs after 2014, early engines earned a reputation for unreliability. Despite the flaws, the Pentastar evolved into a strong performer in later years, especially with direct injection and improved oiling. But for many early owners, it represented a modern engine that could fail catastrophically from a single plastic part. The Pentastar was meant to showcase Chrysler's engineering progress. Instead, it proved how one weak component could bring a modern powertrain to its knees. 2010 Ford 2.3-liter EcoBoost. The 2.3-liter EcoBoost was introduced as part of Ford's turbocharged engine family designed to blend performance with efficiency. It powered vehicles ranging from the Ford Focus RS and Mustang to the Explorer and Lincoln MKC. On paper, it delivered big power from a small displacement, but in practice, it became known for several reliability issues that earned it a troubling reputation. One of the most serious problems has been head gasket failure. Early 2.3-liter engines shared a block design with the smaller 2-liter EcoBoost, but the deck surface and cooling passages didn't perfectly align with the new cylinder head. The mismatch caused localized hotspots between cylinders 2 and 3, eventually blowing the head gasket and allowing coolant to leak into the combustion chamber. This led to white exhaust smoke, misfires, and in severe cases, complete engine failure. The turbocharger system brought its own challenges. Turbo bearing failures and oil coking from heat soak could starve the turbo of lubrication, resulting in loss of boost or a seized unit. Direct injection also caused carbon buildup on intake valves, which reduced airflow and led to rough idling and power loss over time. Ford revised the design in later years with improved cooling passages, updated head gaskets, and better turbo oiling, but early versions, especially in 2015 to 2017 Mustangs and Focus RS models, remained prone to failure. When healthy, the 2.3-liter EcoBoost delivers impressive torque and efficiency, but when its weaknesses surface, they can turn a modern turbo engine into an expensive liability almost overnight. 1996 Chevrolet 2.4-liter Quad 4. The 2.4-liter Quad 4 was GM's attempt to modernize its high-output four-cylinder line for the late 1990s. Used in cars like the Oldsmobile Alero, Pontiac Grand Am, and Chevrolet Cavalier Z24, it promised solid performance and efficiency. But underneath that promise, the engine was plagued by reliability issues that made it one of GM's more troublesome small engines of the era. While early versions of the Quad 4 family were known for head gasket problems, the later 2.4-liter variant wasn't as prone to catastrophic failures as some owners claimed. Head gasket issues did occur, but they weren't the most common failure mode. Instead, most complaints centered around excessive noise, vibration, and harshness, often abbreviated as NVH, along with the timing chain system. The chain tensioner and guides suffered from inadequate oil flow, leading to chain rattle and accelerated wear. In some cases, this resulted in poor valve timing and rough operation, though outright timing chain failure was relatively rare. The coarse mechanical soundtrack of the engine and its high vibration levels gave it a reputation for being unrefined, especially when compared to smoother competitors from Honda and Toyota. GM engineers eventually addressed these shortcomings with the newer Ecotec series, which was far more refined and durable. Yet, for nearly a decade, the 2.4-liter Quad 4 became known less for exploding catastrophically and more for sounding and feeling like it might, a noisy, rough-running power plant that promised excitement but delivered frustration. 2003. Ford 6-liter PowerStroke Diesel. The 6-liter PowerStroke Diesel, built by Navistar for Ford's heavy-duty trucks, is one of the most infamous diesel engines ever sold in the U.S. Designed to replace the reliable 7.3-liter PowerStroke, it introduced more complex emissions equipment and advanced hydraulics. On paper, it was cleaner and more powerful. In reality, it was a reliability nightmare. The core problem was head gasket failure caused by weak torque to yield head bolts. Under boost, the bolts stretched, allowing combustion gases to enter the cooling system. This caused coolant to overheat, overflow, and eventually blow the head gaskets, often catastrophically. Many trucks required expensive, head stud retrofits to fix the issue. The 6-liter also suffered from EGR cooler failure. The exhaust gas recirculation cooler would crack internally, allowing coolant into the intake, and causing white smoke, loss of power, and sometimes hydrolocked cylinders. When the EGR cooler failed, it often took the oil cooler with it, leading to oil starvation and bearing damage. Adding to the chaos were high-pressure oil pump and injector failures. The injection system relied on precise oil pressure, and even minor leaks or sensor faults caused hard starts and stalling. While enthusiasts have learned how to bulletproof the 6-liter with aftermarket parts, the stock design remains one of the most maintenance-heavy engines ever installed in a Ford truck. The 6-liter PowerStroke promised cutting-edge diesel performance, but delivered years of blown gaskets, coolant leaks, and stranded owners. It stands today as a textbook case of over-engineering gone wrong. 1961. Pontiac 265 V8. The Pontiac 265 V8 was a short-lived experiment that never quite met the brand's reputation for strong, torquey engines. Introduced in 1961 as the base engine for smaller Pontiacs and Tempest models, it was designed to offer a balance between performance and efficiency. In practice, though, it proved more forgettable than flawed. Derived from Pontiac's larger 389 cubic inch V8, the 265 shared much of its architecture but used smaller bores and lighter components. This scaling down worked in theory but exposed some weaknesses in sealing and oil control. Oil leaks were a frequent complaint, particularly from the rear main seal, valve covers, and pan gasket areas, but claims of catastrophic bearing, starvation, or widespread internal failure are largely overstated. Most engines simply seeped or burned oil without total mechanical collapse. Cooling and sealing issues did occur occasionally, but they weren't epidemic. Instead, the 265's biggest shortcoming was its modest performance. With low compression and limited breathing capacity, output hovered around 120 to 140 horsepower, leaving smaller Pontiacs feeling sluggish compared to rival compacts from Chevrolet or Ford. It was an engine that did its job, barely, but inspired little enthusiasm. By 1963, Pontiac quietly dropped the 265 in favor of more robust and better performing small V8s. In retrospect, it wasn't a deadly engine, so much as an unremarkable one, underpowered, leaky, and quickly forgotten in the shadow of Pontiac's legendary performance motors that followed. 1966. Dodge 440 Magnum V8. The Dodge and Chrysler 440 Magnum V8 was one of the most powerful engines of the muscle car era, but it wasn't without serious flaws that showed up under real-world driving conditions. Introduced in 1966, the 440 was a high-compression big block built for performance models like the Charger RT, Roadrunner, and GTX. When tuned right, it was a powerhouse. When pushed too far, it could destroy itself. The engine's biggest weakness was detonation at high altitude or under heavy load. Its high 10.1-to-1 compression ratio demanded premium fuel and precise timing. At altitude, with thinner air and lower octane gas, detonation could occur, spontaneous combustion that shattered pistons and hammered bearings. The problem worsened as emissions regulations forced leaner fuel mixtures and retarded timing, creating unstable combustion and excessive heat. Block cracking was another recurring issue, especially on engines that overheated or saw repeated high revolutions per minute abuse. The cast iron block's thin walls in some late 1970s versions couldn't always handle thermal stress, leading to cracks in the lifter valley or water jackets. Despite these problems, the 440 Magnum remained a legend for its sheer torque and durability when maintained properly. But by the late 1970s, lower octane fuels and tightening emission standards exposed its fragility. The 440 Magnum was both brilliant and flawed, a symbol of Detroit excess whose engineering couldn't adapt to changing times. Under ideal conditions, it was nearly unbeatable. Under the wrong ones, it could turn from muscle car hero to mechanical time bomb in seconds. 1977. Oldsmobile 403 V8. The Oldsmobile 403 V8 was a late 1970s attempt to deliver big block torque in an emissions-constrained era. Found in cars like the Trans Am, Delta 88, and Custom Cruiser, it was built for smoothness and power at low revolutions per minute. But while it looked good on paper, its internal design created serious durability problems that made it one of Oldsmobile's more failure-prone engines. The biggest flaw was the Siamese cylinder design. To meet emissions and manufacturing goals, Oldsmobile cast the cylinders without coolant passages between them. That reduced heat dissipation and caused severe hotspots under load. Combined with thin cylinder walls, the engine ran hot even in normal driving. In warm climates or when equipped with air conditioning, overheating was almost guaranteed. The constant heat led to bearing wear, head gasket leaks, and warped heads. The 403 also used windowed main webs in the block to save weight, but that made it structurally weaker. Hard driving or sustained highway speeds could cause crankshaft flex, leading to bearing failure or even block cracking. Oil consumption was another persistent issue. The engine's poor ring sealing and heat-induced wear meant that many 403s burned oil after just 50,000 miles. Despite these problems, the 403 produced decent torque and remained popular in full-size cars, but its fragile design couldn't survive sustained heat or heavy load. The Oldsmobile 403 stands as a product of its time, an engine forced to chase emissions and efficiency goals at the expense of strength, leaving behind a legacy of overheating, oil loss, and early death under pressure. 1970. Pontiac 455 V8. The Pontiac 455 V8 represented the final evolution of Pontiac's legendary big block family, a torque monster designed for raw power rather than high revolutions per minute performance. Introduced in 1970, it produced as much as 370 horsepower and 500 pound-feet of torque in its early high-compression form. But as emissions and fuel regulations tightened, the 455's reliability and cooling system design started to show major weaknesses. The engine's most persistent problem was oil delivery and bearing failure. Pontiac's oiling system sent limited flow to the crankshaft and rod bearings, especially at sustained high revolutions per minute. Under heavy throttle, oil pressure could drop enough to starve the lower end, wiping bearings and damaging crank journals. Combined with wide main bearing clearances, the 455 was extremely sensitive to oil viscosity and maintenance neglect. Cooling system inefficiency compounded those issues. The engine's large bores and Siamese cylinder walls made it difficult to dissipate heat evenly. Overheating led to head gasket leakage, valve guide wear, and water contamination in the oil, a recipe for bearing failure. Even under ideal conditions, the 455 tended to run hot, and once it overheated, it was prone to warping and leaks. By the mid-1970s, Pontiac detuned the 455 for emissions compliance, but the reliability concerns persisted. It remained powerful but fragile, a big engine designed for a different era. The 455 is still revered by collectors for its torque and muscle car heritage, yet mechanically, it serves as a reminder that brute force without balanced engineering can lead to a short, violent lifespan under the hood. 1968. Chevrolet 307 V8. The Chevrolet 307 V8 was introduced as a practical and efficient evolution of Chevy's small block family. Combining the 283's bore with the 327 stroke, it displaced 5 liters and was designed for smooth operation, decent fuel economy, and low emissions in full-size sedans and smaller performance models. On paper, it was a smart middle ground between displacement and efficiency. In practice, it was simply unremarkable. The 307 shared the same basic architecture that made Chevrolet's small block V8s legendary for reliability. While minor oil leaks from areas like the rear main seal and valve covers weren't uncommon, they were more a nuisance than a sign of poor engineering. The engine wasn't notably failure-prone. Most 307s ran reliably for many years with routine maintenance. Claims of weak internals or chronic oil starvation are largely exaggerated. Its real limitation was performance. With low compression ratios and conservative factory tuning, the 307 produced modest horsepower and torque compared to its larger siblings, the 327 and 350. It was smooth and dependable at everyday speeds, but uninspiring under acceleration. Enthusiasts found little reason to modify or race it, and its mild character meant it was overshadowed by the more iconic Chevy small blocks. Ultimately, the 307 wasn't a bad engine, just an ordinary one. It delivered acceptable economy and longevity but lacked excitement or standout features. History remembers it not for failure, but for being the definition of average in an era when Chevrolet built some of the most celebrated V8s in the world. 1986. Ford 3-liter Vulcan V6. The 3.0-liter Vulcan V6 was one of Ford's longest-running engines, used in vehicles like the Taurus, Ranger, and Aerostar. It earned a reputation for simplicity and durability when properly maintained, but it also suffered from chronic design issues that often turned dependable daily drivers into maintenance nightmares. At its core, the Vulcan was an old-school pushrod engine designed for low-end torque and ease of service. However, timing chain wear was a recurring problem, especially in higher mileage engines. The single chain tended to stretch and lose tension, leading to rattling, poor timing, and reduced performance. If ignored, it could skip a tooth and cause valve to piston contact. The engine also struggled with coolant leaks from the timing cover gasket. As the gasket aged, coolant seeped into the oil pan, contaminating the oil and causing bearing wear. Combined with head gasket failures in later variants, particularly those used in the Taurus, these leaks led to overheating and oil sludge buildup that could ruin the engine. Though the Vulcan was relatively simple and cheap to repair, its tendency to leak, overheat, and lose timing precision earned it mixed reviews. It was durable under ideal conditions, but unforgiving if neglected. By the 2010s, its outdated design couldn't compete with newer overhead cam engines. The Vulcan's legacy is split, remembered by some for its toughness, but by others as a relic that leaked, rattled, and overheated its way out of the modern era. 1970. Oldsmobile 455 V8. The Oldsmobile 455 V8 was one of the largest and most powerful engines of the early 1970s, known for its effortless torque and smooth delivery. Found in cars like the Tornado, 442, and Delta 88, it was built for brute force performance. But, despite its strength, the engine carried fundamental design flaws that led to severe durability issues when pushed beyond normal use. The most significant problem came from oil pressure fluctuations in its high-volume oil pump. The 455's pump relief valve could stick or fail to regulate pressure properly, starving the lower bearings during sustained high-speed driving. That inconsistency led to bearing, scoring, crankshaft wear, and eventual engine failure. For performance drivers, this often happened without warning. The gauge would show normal pressure one moment, then zero the next. Cooling was another weakness. The 455's thin cylinder walls and poor water jacket circulation made it prone to overheating under load. In heavy cars or hot climates, detonation and warped heads were common. The combination of heat and poor lubrication also caused premature camshaft wear, especially on engines running low-zinc oils. Even with its flaws, the 455 remained a legend for its power and low-end torque, producing over 500 pound-feet in early high-output versions. But as emissions restrictions tightened, compression dropped, and reliability concerns grew. The Oldsmobile 455 became a symbol of 1970s excess, powerful yet fragile. Its oiling and cooling shortcomings ensured that while it could dominate the quarter mile, it rarely survived decades of hard use without serious internal damage. 1962. Chevrolet 350 Small Block. The Chevrolet 350 Small Block is one of the most celebrated engines in American automotive history. Introduced in 1967, it became the gold standard for durability, simplicity, and performance potential. Over the decades, it powered everything from family sedans to Corvettes, pickup trucks, and even boats, cementing its place as the most recognizable V8 ever built. Despite its legendary status, some misconceptions have surrounded the 350's supposed weaknesses. Many issues blamed on the 350 actually stemmed from the drivetrains it was paired with, particularly the rear differentials that used clips to retain axle shafts. When those clips failed, the rear wheels could detach entirely, but that was a rear-end design flaw, not an engine problem. The small block itself remained exceptionally reliable when maintained properly. Inside the engine, true mechanical failures were relatively rare. Some early versions experienced minor oil pressure fluctuations or bearing wear under extreme neglect, but these cases were exceptions. Most 350s easily ran for hundreds of thousands of miles, thanks to robust cast-iron construction, straightforward lubrication, and forgiving tolerances. Even during the emissions-restricted 1970s, the 350 maintained a balance of torque and efficiency that competitors struggled to match. Its simplicity made it the go-to choice for hot rodders, restorers, and racers, a power plant that could be tuned for anything from daily driving to drag strip dominance. The Chevrolet 350 remains a symbol of mechanical dependability. It wasn't flawless, but its few minor quirks were far outweighed by decades of proven strength, making it one of the most enduring and trusted engines ever built.